is the input from the function.
Very good, very good. So what's the output? Phi inverse. What's the input to phi inverse?
Is the real numbers?
Rn.
Rn.
Right. Very good. So this is the input to the entire thing. Now the output here is a point on the manifold. F takes a point on the manifold and gives you R.
Okay.
So when you do them simultaneously, not simultaneously, consecutively actually,
okay.
then you take up, this means that the input is a point on Rn and the final output will be a point on R.
Okay.
So this composite map is from Rn to R, and actually this is called the local representation of F, in the sense, how are you going to write F in coordinates? This is like F in coordinates. The coordinates are provided by the phi, so if I want to write your temperature function on the Earth, if you want to write it in terms of phi and theta, the cylindrical coordinates, okay, the longitude and latitude, you want to write it in coordinates. How are you going to do that? This is actually F composite with your local chart. So this is F of x1 up to xn. It's as if you just do it, if you're going to write a function, well, in an expression in terms of coordinates, this will be the thing, right? And just make sure that this is differential in the sense that you are aware of in real analysis. And we'll do this thing for almost everything. So let's talk about a function from M to N. These are two manifolds. Why do you care about functions, differentiable functions? Because actually differential geometry is all about differentiable functions and manifolds. So in topology, you study continuous functions on open sets, right? In real analysis, you study differentiable functions on real. In complex analysis, you study holomorphic functions, right? On C. And here in differential geometry, we study differentiable functions on manifolds. In algebraic geometry, for example, you study regular functions, which is ratio polynomials, okay, on algebraic sets. This is basically what we do. So mostly our course will be, or at least the differential geometry part of the course will be mostly concerned with differentiable functions. Here, our manifold, now I have just a scalar function, takes a point on the manifold and gives me a real number. Then we will go up one more step. So I have a function between two manifolds. And in the back of my head, I know that this is phi, this is r, m, maybe because this is maybe a different dimension, rn, this is a psi inverse, phi inverse, okay? And I have a map between them. Can you tell me how to define the differentiability of f? If from m to n is differentiable, if what? Can you tell me? Any suggestion? Differentiable if what?
With the map from
psi minus 1 f.
Very good. Phi minus 1 f and then psi. This is a map from where?
Yeah. This is from Rm to Rn.
Rn, and I know very well how to define differentiability with this guy. And I know very well how to differentiate it, actually. So this is what we call the local representation. Local representation. If these are y's and these are x's, then f provides you the mean to relate y to x. So if you want to write y1 up to yn as functions of x1 up to xm, this is the thing. And you just check if this guy is differentiable.
Professor, I have a small question.
Sure.
Regarding, so we were not able to define differentiability on the manifold.
On the manifold per se. This is defining differentiability on the manifold.
Yeah, I just had.
By just relating to the Euclidean space.
So if we could define an alternative definition that if I add 2 points on the manifold and then project the result back to the
Then
to
you
the
are
manifold.
resorting to the ambient. This, yeah, so the main point is that this is not resorting to the ambient. If you prefer, so differential geometers, I mean, all their work is to prevent this thing, right? Is to, maybe this is a good thing, it's not arguing at all. I mean, they actually
Do they
prefer
get the
this
same
thing.
result?
But all their work, the entire, branch of differential geometry is to prevent this thing, is to prevent that you know what? My thing is embedded in a higher dimension space. I will do it in the higher dimension space and project back. Well, you can do that. But the entire differential geometry is to avoid that. Is to do it on the manifold without resorting to the fact that you are already embedded in a higher dimension space. We don't need to do anything in the higher dimension space.
Why?
We will do it on the manifold. Yes.
Why, Professor?
Why we don't want to do it in the manifold?
Yeah, why the entire branch?
I mean, to focus on the intrinsic properties of your manifold, not to be distracted by the ambient space, obviously. What do you mean? So, there is a debate in the community in the following sense, because there is a theorem, Whitney embedding theorem, that says that every manifold is embedded in a higher dimension space. But this higher dimension space could have, could be much larger, and you would be really distracted by doing calculus in a much larger space than just doing it in the manifold.
Do we get the same result?
It depends on the projection, how you're going to do it. Certain types of projection, yeah, you'll get the same result. So, can you give me an alternative here? Or still, we are doing it on the manifold, just by the knowledge that we just got. So yeah, I mean, this is one way. And knowing the fact that I may have actually functions here, that little functions g that maps to r. And I know how to define little function to be differentiable. Just go up one little thing. We know how to define a function, little f or little g, that takes a point on the manifold. We know how to define the differentiability of it. So I know already if g is differentiable or not. Okay, don't worry about that. Can you give me an alternative definition for the differentiability or logic? We have a definition in terms of these local charts. That's right. Can you give me a definition in terms of this guy? Well, if I compose little g with this logic, this will be a map from where to where?
From M to R.
Exactly, very good. So this will be something like, this is g composed with f. So this is a function on M, right? So g composed with f is a function on M. So f is differentiable f for any differentiable g on N. We have this guy is differentiable as a map from M to R, right? So this is OR, okay? We have this definition, OR definition. In particular, we have a very important map between manifolds. What is this? This is the definition of a curve. And this is the last thing I will do here. A curve. What's a curve? So I have a manifold, and manifold means that, this is your Rn, this is phi inverse. I may have some functions to the real, so this is little f, this is R, and here is my curve. A curve takes the real line, typically a closed subset in the real line, I in R, and map it to your space, gamma. So typically the variable here in R, sometimes or typically we denote it by little t. You can consider as time if you like. As t moves, so gamma takes a point in here in the real line and gives you a point on the manifold. And as t moves, the point on the manifold moves, so it looks like a curve. Okay? So gamma takes I, which is an R, and gives you a point on the manifold. Can you give me a definition for its differentiability? Is differentiable if what? This is a special case of the previous case. Why? Because it's a map between two manifolds. Obviously, This guy is a manifold, and M is a manifold by definition. So it's a map between two manifolds. Can you give me a definition? Yeah, if first. Any suggestion?
Well, compose gamma with phi and phi.
Yeah.
Sorry.
Phi. So phi composed with gamma. Phi composed with gamma. This is a map from
From the interval.
R, right, to
Okay.
Rn. Actually, this is like I always say, this is the local representation. Local representation. What do you mean? In coordinates. So phi composed with gamma. Phi composed with gamma looks like the following: x1 of t, right, up to xn of t. So when I write in coordinates, this is how it would look like. And just check if this guy is differentiable or not. Or if you want to do it the other way around, that you compose what with what? Gamma with all these f's. So for all differentiable f on M, the map f composed with gamma, which is from the real to the real, this is super easy to check, is differential.
But this is not a practical condition because I cannot check all differential functions.
I mean, you're coming with a definition. Any differentiable function, no, you can do it using the elementary stuff. So for any function that satisfies the condition of differentiability, and you have a condition, then is this guy differentiable or not? You will not bring any function to all the
Yeah, I
functions.
mean, I have to check all differentiable functions, right?
That's right.
And compose them with the curve and check that all
That's right.
differentiable functions are.
The same here.
No, but I just
The
need
same
to
here
have-
for any phi. Give me any phi. I don't know, I mean,
It's the local chart, right?
any phi, yeah, any local chart, that's right. But
But-
any phi, this means that, I mean, I can define my phi's in a very arbitrary way, right? You have freedom. All what you know is that they are diffeomorphisms. The same here, all what you know is that these guys are differential.
But for phi and gamma, if I came up with an atlas, I just need to check that the curve, that the
No,
composition
not for this particular atlas only. For any, that's what I'm saying. For any.
for all atlases.
Yeah. So which is again is very generic. Just want to give a definition here, or not a definition, just a notation, because we're going to use it a lot. Of this guy, it's this the green, it's different. Okay. This guy, the composition, because it has a name. We'll use it. So this was, yeah, okay, I've got 5 minutes. We'll not use the 5 minutes. So this is N, this is F, this is M, this is G to the real, and this guy is G composed with F, right? So if this is differentiable, then we call G composed with F, sometimes we denote it by F star G, is the pullback of G along F. The name comes from the following: G acts on N. So it's as if you pull it back to N. Now, this guy is a function that acts on N. Okay, that's just a notation, nothing more. We will be very interested in differential curves. So these guys, if they are differentiable, then we will go and really differentiate them to get x1 dot of t, x, right? X dot of t. This is what we call the velocity of the curve, right? The velocity of the curve is a vector, and this is one of the things where really differential geometry will become quite different from working with green analysis, because in Euclidean space Rn, what is a point? P? Well, it's like x1 up to xn, so it's an n of bunch numbers. What is a vector? V? Well, I'm sorry, it's also a bunch of n numbers, but they are very different entities. This is really a vector, it's a velocity vector, You can add velocity vectors, right, to get faster or whatever. I can scale the vector, but here, I mean, in general, I cannot necessarily add points, like I said on the manifold. So a point is fundamentally different from a vector. In Euclidean space, we look at them in the same way. In manifold, they live in different spaces actually. Point obviously is on the manifold. This guy, we don't have vectors on the manifold, so we need to come up with a new space, which you guys may be aware of, that is the tangent space that we talked about in the lecture. So this is the topic for next time, tangent space and tangent vectors. Any questions so far? Any questions about the homework? I mean, you had a homework, we have a couple of minutes, you can discuss the homework. Did you bring the homework or not? I mean, this is, that's like 40% for the homework, right? Do you have a question about the homework? Because we relied on the online lecture.